Today I'd like to discuss the law of conservation of angular momentum, which is a separate conservation law, not to be confused with the law of conservation of linear momentum. Okay? You can't really combine the two. They're two separate conservation laws. Whereas with the law of conservation of energy, you can have rotational energy and translational kinetic energy combined into the same conservation law of energy. Not for conservation of angular momentum. It's separate. Okay, well, let's take a look at an example of the Earth orbiting about the Sun. You can see in the drawing here that the Earth with mass m, its northern hemisphere pointed toward the upper left, toward the North Star Polaris. On June 21st, the Earth is a little bit farther away from the Sun than it is on December 21st, and it's going slower. So this small v means it's going slower in its orbit, its tangential velocity, whereas on December 21st, the Earth is moving much faster in its orbit. Its translational velocity is much bigger. Okay, why is that? Well, because of the law of conservation of angular momentum. Let's look at the relationship here. Angular momentum symbol is capital L, and the equation for angular momentum for a particle, we can treat the Earth as a point mass, would be r, which is the position vector, cross mv, where v is a translational velocity. This is very similar to the idea of torque being equal to r cross f. So recall that torque is equal to vector r, the position vector, cross f. And remember what that equals. That equals the magnitude of vector r times the magnitude of vector f times the sine of the angle between the two vectors. Well, it's the same kind of idea for this. Okay, this is a vector cross product, just like torque is. And so angular momentum then would be equal to r times mv, the magnitude of r times the magnitude of mv, times the sine of the angle between. Now if you look up here, the angle that we have between vector r and vector v is 90 degrees. And the sine of 90 degrees is equal to 1. So therefore, in the case where the position vector and velocity vector are at right angles to each other, you just end up with r times mv for the angular momentum. Okay? Now, in the case of the Earth going around the Sun, notice that we have a smaller velocity at this point in its orbit and a bigger velocity here. Well, what's the trade-off? The trade-off is that there's a bigger position vector here and a smaller one here. And so we have the conservation of angular momentum means that the angular momentum in position 1 is going to be equal to the angular momentum at some other position 2. So if this is position 1 here, and here's position 2, we can say, okay, the angular momentum here would be that small vector r times the mass of the Earth times a big velocity, that's equal to the angular momentum of the Earth at position 2, which would be a very large position vector r, times the mass of the Earth, times a very small translational velocity. So you can see if the position vector increases, the velocity decreases. And this is a direct result of using the law of conservation of angular momentum. So again, I think that might have been below the screen. If the position vector increases, the velocity, tangential velocity, decreases. A direct result of the law of conservation of angular momentum. Now this kind of formula here, this formula for angular momentum works really well for point masses, where we have the Earth acting as a point mass, traveling with translation velocity v, okay, a certain distance away, okay. But what about for a large mass made up of many particles, like say for example an ice skater? Okay, we can treat the ice skater as made up of many particles pivoting around an axis. Now let's say that the ice skater with her arms extended is twirling about with a small angular velocity v. Now she brings her arms in, and immediately, almost like magic, her angular velocity increases enormously. Okay? Well, what happened? What happened was that when she brought her arms in, she reduced her moment of inertia a lot. And so therefore the trade-off was that her angular speed was able to increase in response. So if we think back to the equation for angular momentum, which was r times m times v times the sine of the angle between, that would work real well for point mass, single point mass. But for this situation where we can actually figure out what the moment of inertia would be, a different form of the angular momentum equation is more useful, and that would be angular momentum is equal to the moment of inertia I times the angular speed omega. So depending on the type of problem you're going to be doing, you're either going to be using the formula that I showed you, which is useful for, say, the Earth going around the Sun. But in this case, the second form here of the formula is much more useful. Okay? So let's see how that would work here. In the case of the ice skater with arms extended, there's more mass concentrated farther away from the pivot, the axis of rotation, so therefore the moment of inertia is big here. In the case of the ice skater who moves her arms in, she reduces her moment of inertia by a lot, and so therefore the angular velocity or angular speed increases enormously. Let's see how that works with the law of conservation of angular momentum. Okay? That means that we have the angular momentum before, let's say in position at point 1, that's going to be equal to the angular momentum after, which would be, say, at point 2. So this would be 1, this would be 2. Okay? Remember, we're going to use this form of the angular momentum equation. Angular momentum equation. So in this case here, we have a large moment of inertia times a small angular speed. That's going to be equal to a small moment of inertia when she brings her arms in, and the resulting angular speed will be very large. Okay, so conceptually, you can see how these two equations work. This one is appropriate for the Earth going around the Sun and problems where you have particles that you can treat as point masses. And this second one is good for particles where you know the moment of inertia of a composite object, and you can use that. Okay, let's take an example of a problem, and I will work that out for you. I took this problem from Young and Friedman's 2013 textbook. Very excellent textbook, by the way. I highly recommend it. And this one, we're dealing with a bullet that's going to hit a door. This is a top view looking down on a door. The bullet's traveling toward, and going to hit the middle of the door. It's going to stick in the door, and the door is going to swing open. The mass of the door is 15 kilograms. The mass of the bullet is 1/100th of a kilogram. The velocity of the bullet is 400 meters per second. The door is 1 meter wide, and the bullet hits at a distance of ½ a meter from the hinge. So I'll just use that little L for that. Okay? This is going to be an inelastic collision. An inelastic collision. Okay? Now, the question basically asks, find the door's angular speed. So that would be omega. Okay? And I'd like to ask you to also find the amount of kinetic energy before the bullet hits the door and after the bullet sticks in the door, and then compare the two kinetic energies. And usually when I ask you to compare, that means divide to see how many times bigger one is than the other. I'd also like you to find, or I'm going to show you how to find the time needed for the door to swing 90 degrees. Okay, so those are the questions we're going to address in this video. Okay. Now, since this is a collision problem, and since we have a rotation here about this hinge, it's going to rotate like that, right? This is a job for the law of conservation of angular momentum. Okay. So remember that here. I'll just separate what we want to find, and now we'll go ahead and get started. Remember the law of conservation, I'll just abbreviate, of angular momentum means that the total angular momentum before the bullet hits is going to be equal to the total angular momentum after the bullet hits. Now let me ask you this question, have you think about it for a second. This bullet that's traveling toward the door before it hits it, does that bullet have angular momentum? And the answer is yes, it does. Amazingly, okay? We can treat this bullet like a little point mass and use that first form of the equation for angular momentum for that bullet. Okay, does the doorway have momentum, angular momentum, before the bullet hits it? And the answer is no, because the door, I forgot to mention, is at rest. The door is at rest before the bullet hits. Let me write that in right here. So, okay. So, what would the bullet's momentum be before? Well, it's going at 90 degrees from the doorway, so therefore sine of 90 is 1. Sine of 90 degrees is equal to 1, so we can just use, remember, angular momentum is equal to mass times velocity times the position vector, the distance. So for the bullet, before it collides, it would have this angular momentum of 0.01 times 400 for the velocity times a distance of 0.5 from the hinge, and that equals 2 kilogram meters squared per second. Okay, so that's the bullet's angular momentum before it hits. So that's 2. Now that's for the bullet. What about for the door? Well, like I said, the door is at rest, so it doesn't have any angular momentum before the bullet hits. So it's 2 plus 0. This is the total momentum before the bullet hits the door. Now after the bullet hits the door, we're going to have the bullet will be embedded in the door. And so we're going to have a composite here. And so what would probably be more appropriate is to use the formula for angular momentum, which deals with a composite body, which has a known moment of inertia, times the angular speed. And in fact, we want to find angular speed omega, so this would be a good form to use for the momentum after collision. So we need to think about what would the moment of inertia be. Okay, so let's look at just the moment of inertia here. The moment of inertia of the door, and the total moment of inertia would be the moment of inertia of the door plus the moment of inertia of the bullet stuck in the door. Now if I look up the moment of inertia for a thin slab, pivoting about the end of the slab like this one is here, here's the thin slab, it turns out that the moment of inertia for the thin slab, the door, would be 1/3 m, mass of the door, times L squared. For the moment of inertia of the bullet, which is a point mass embedded in the door, that's just m little l squared. Little m little l squared. So that would be the total moment of inertia of both the door plus the embedded bullet. Okay? Now if we go ahead and substitute those numbers in, get 1/3 times 15 times 1 squared plus 0.01 times 0.5 squared. Sorry, the handwriting's poor. And we end up with the total moment of inertia equals 5.0025 kilogram meters squared. Okay, so we need that here. Okay, so remember that we're using the form L equals I omega, so this would be, let me just do it in red here. This would be L total, I total times omega. I total, we found, is 5.0025 0.025. And we want to find omega. So we can set this equal to this. So the total angular momentum before the bullet collided with the door was 2, and that's equal to 5.0025 omega. So therefore, solving for omega, okay, we get 2 over 5.0025, and that's equal to 0.4 radians per second. So that is the angular speed of the door and the bullet as the door swings open. Okay? So that's the answer to the first bullet here, the door's angular speed. This is the angular speed of the door swinging open. Okay, now the next question is, what's the amount of kinetic energy before and after, and compare? Okay, well, let's look at the kinetic energy before. That's just the kinetic energy of the bullet, which is 1/2 mass of the bullet times velocity of the bullet squared. So that's 1/2 times 0.01 times 400 squared, and that equals 800 joules. How about the kinetic energy after the bullet sticks in the door? Okay, well, now it's a rotational problem. You have, and that would, so therefore the kinetic energy of rotation is 1/2 I omega squared. Remember that we found out that I total was 5.0025. So this will be 1/2 times 5.0025. And we found out that the angular speed was 0.4 radians per second. And we're going to square that. And when we do the math, it comes out to be a measly 0.4 joules. So now if we compare the kinetic energy before with after, or maybe we ought to do it the other way, comparing kinetic energy after to that of the kinetic energy before, we see that this is 0.4 joules over 800 joules, which gives us 1/2000th as much kinetic energy after compared to before. So only have 1/2000th of the original kinetic energy of the bullet. So look at how much energy was lost in the form of heat. Okay, so that's pretty amazing. We knew that it was going to be some loss, right? Because it's an inelastic collision, and you don't have kinetic energy conserved for an inelastic collision. But that's a lot of energy lost to heat. Okay, as that bullet is burrowing into the wood, it converted a lot of that energy to heat. The last part of the question was, how much time is it going to take for that door to swing open to 90 degrees? Okay, well, remember that 90 degrees is the same thing as pi over 2 radians. So if we take our pi over 2 radians and multiply it by the fact that we had 0.4 radians per second, we need to flip that, and so that'd be 1 second for every 0.4 radians. We flip it so that the radians will cancel. I know, radians aren't a unit of measure, and so we really shouldn't have to worry about that, but it's helpful to visualize that. And then we're going to be left with seconds remaining, which is what we're looking for. We're looking for time. So if we go ahead then and solve this, we end up with the time needed is 3.93 seconds for the door to swing open 90 degrees. Thanks a lot, everybody.